Hello everyone. This is a 10 minutes presentation of our paper in which we introduce a refilling water bottle scenario in elderly care homes with a safe service robot. Today, the shortage of care workers in combination with different side tasks limits the time for human care. Our scenario supports the staff in the refilling of water bottles to exemplary demonstrate how service robots relieve care workers. The presented paper shares the results and experiences that we made in deploying the robot within a 2-week test in a care home. The following video shows the robot routine between the refilling station and a resident's room. The scenario starts manually by a person, but the rest is autonomously done. Care staff sends the robot to a resident's room. The robot searches for empty water bottles on tables. The robot safely grasps the detected bottle and carries it to the kitchen. The robot brings the refilled bottle back into the room. We chose the mobile service robot CareObot 4 for demonstrating the application as we've had extended experience working with it in similar applications. In its basic setup, the robot consists of an omnidirectional platform and two 6 degrees of freedom manipulators. It comes with several safety features, such as safe emergency stop buttons and laser scanners. However, the initial hardware setup lacked the capability to sense objects that extend above ground level. Therefore, to comply with the high requirements for safety in an environment where vulnerable people will encounter the robot, we made some hardware changes. Our redesigned robot head enhances the detection capabilities of the robot. It is equipped with up to 2 sensors, for example, RGBD camera or radar sensor, which can be tilted. This way, we can prevent the robot from getting into critical situations by sensing those in time. As the previously deployed manipulators had no collaborative safety functions, we integrated new manipulators from F&P Robotics. They come with a soft cover that minimizes the force of a possible impact and detects any collision, and stop immediately. The environment model of the robot consists of multiple components comprising the recognition and registration of spatial information with its semantic, the storage of knowledge, and a service interface to provide environment information. Initially, the approach uses the open-source 3D simultaneous localization and mapping, SLAM, to reconstruct the spatial scene. The registered 3D point clouds of the SLAM are processed further to extract the semantics of primitive environment structures based on planes. A document-based database stores and organizes the planes. Our scenario uses the table to search for the bottles in the rooms. Furthermore, point of interest realized by interactive markers extend the recognized scene information. They are helpful within development and testing to easily mark needed poses such as the charging or idle pose. The robot needs to detect the bottles to fulfill its scenario. Unfortunately, the bottles used in care home were mainly transparent, as seen on the right side, and we could not collect many photos of them. That is why, we created a 3D model of the bottle. The 3D model is rendered with random backgrounds with random lighting conditions. This data is used to train the second stage classifier. Our detection system is a 2-stage system. The first stage is a pre-trained network from the literature that detects the bottles. Next, however, we need to filter only our bottles. So, we trained a classifier trained with our synthetic dataset to classify if the bounding box coming from the detection is our bottle or not. We need the 2D bounding box and reliable pose estimation to finally grasp the bottle. To stick with the modular approach of our perception pipeline, we have separated the pose estimation, but made it use the results from the previous steps. Hence, it just estimates poses for the areas which have passed the fine bottle classifier filter. Following the idea of keypoint estimation, it locates the discriminative top part around the lid, and the bottom part of the bottle. As the bottle is rotational symmetric, these 2 keypoints are enough. Combining the keypoint results with a known 3D object model provides the pose. This hypothetical pose is then verified by a simple collision check using the plane of the table from the environment model. A grasp planning and manipulation are two main components for handing bottles. We used model-based grasp planning approaches to generate valid grasp points with a given bottle position and bounding box. For grasp points validation, we selected two grasping criteria. First, we considered that the end effector won't crash with other bottles in the environment. The second one is sorting grasp points according to preferred grasp angles. While a robot arm manipulation consists of two main parts, motion planning and motion controlling. Motion planning is sometimes known as trajectory planning, which generates constraints, position, orientation, and joint, and collision-free trajectory. We chose Rapidly Exploring Random Tree Single Query Motion Planner from the Open Motion Planning Library. It is one of the most popular planner frameworks used with MoveIt. While motion controlling uses a PID controller to execute the point-to-point trajectory generated from the motion planner by considering constraints such as path and goal tolerances. First, let us start the evaluation with the bottle detection results. Although we had a 91% accuracy on our test set, the accuracy dropped significantly during the actual test due to the repetitive conditions of the robot. So we introduced the shake it until you make it approach to avoid these repetitive conditions, which got an accuracy of 90%. We recorded the error types causing an interruption of the scenario. Due to parameter optimizations, some errors like grasping the bottle improved over time. However, door passing is an example of consistent error because it needs hardware changes. The number of data points seems low, however, in a real test, the allowed working hours of the robot are quite limited, and if there is no empty bottle, we cannot run the scenario. We segmented the scenario into 6 temporal segments and recorded the time of each segment. Exchanging a bottle takes around 13 minutes. The time mirrors that the robot is slower than a human. If we optimize the robot for time and speed up with the current setup, it would scare the people, although it is safe. Sometimes, the safety field and the door overlapped, causing the robot to activate the emergency stop. In other cases, the robot entered the door after several retries. Similarly, the robot loses time when it cannot detect or grasp the bottle directly. A significant advantage is that the time spent during each component is foreseeable. For example, some parts, like dropping the bottle, vary only by 5 seconds. The lessons learned are divided into hardware, software, and others. On the hardware side, smaller circular bases ease passing through narrow places. Also, we advise placing 3D cameras on all faces of the robot to avoid obstacles. Finally, an application-specific gripper is necessary to grasp the items confidently. On the software side, generic error fallbacks and dynamic object avoidance are beneficial for handling unexpected situations. In addition, the robot's speed is adjusted so that it won't scare anybody. Sometimes, it is hard to understand the robot. So, an intuitive communication system would increase understandability. Finally, we suggest coordinating with the care home as early as possible due to the preparations. Also, the number of staff around the robot could be minimal, so inviting others on the test days would help get more opinions. Thank you for listening.